the exit question yesterday, what is a force? So I got a bunch of different answers. Some people who had something close to what I thought it was. Some people had something else. Just tell the person you're sitting next to what you think the definition of a force is. And then I'm going to share with you what I think the definition of a force is. So go ahead and talk to each other just for about 30 seconds. All right. So, a good definition for this class for force is, we call something a force if it exerts a push or a pull on an object. So we use the word object just as a generic word on, an object. We use the word object as just a word that could be like anything that is a thing. So that's what is a force. And another question that we want to answer today is, what are the different types of forces? So these would be like essential questions that are going to guide our note-taking today. So I just want to share with you the different types of forces. And so it's called free body diagrams because eventually we are going to learn how to use free body diagrams, which are an important tool for our investigation into Newton's second law and how things experience a net force, which is the standard that we have to be able to master for the state test. All right, so the first force that we're going to talk about is the force of gravity, and its symbol is capital F with a little g as a subscript. So this force is the force of gravity, and it's got another name, which is weight, also known as weight, aka weight. So weight is the common language word. Force of gravity is what I want to call it. Cody, I really can't take questions when I'm recording. Okay. Its direction, so force of gravity points towards the center of the earth. Its direction is towards the center of the earth. And so that would look like this, down towards the center of the earth, an arrow that points down. So Isaac Newton is the person who is credited with our understanding of this force, or our basic understanding of this force. And he was a pretty smart person who lived in England in the 17th century. And he did a lot of work in physics and math. But what he did for us today is he gave us, he's the person who figured out what the force of gravity is created by. So the force of gravity depends on, so this is going to be a formula. We're not going to use this formula in this unit. This is a formula for later on in the year, like in January or February. But the force of gravity, so I'm leaving a big space here because I'm going to put something there. It's related to the mass of the planet you're on. And so the mass of your planet determines how much force of gravity is on you. And another thing that determines how much force of gravity is on you is how far away you are from the middle of that planet. And then the third thing is your mass. So big M, little p is the mass of your planet. And little m is your mass. That's your kilograms, not your pounds. And r is distance to center of planet. And we're squaring it. But we'll learn that that square is something pretty special in January or February. And we're missing one letter, and that would be a big capital G. Big capital G is a constant that pulls it all together and makes this an equal sign. It's not to be confused with little g. Little g is the acceleration due to gravity, which we're going to learn about in this unit. Due to gravity, it's equal to 9.8 meters per second squared. Right? Little g is an acceleration. It's a change in velocity. Big G is a constant. It's a number with these weird units. So you don't use the letters interchangeably, because big G means something completely different than little g. All right. Well, people, Cody, did you have a question?
Yes. I thought weight was how much mass something has.
Oh, you know what? That is actually a very good question. Mass is not equal to weight. No. Mass is how much stuff you're made out of. Mass is how much stuff. And that's measured in kilograms. And your weight, which is force of gravity, is your mass times your acceleration due to gravity, which is measured in newtons.
So whenever you step on a weight scale,
You're measuring your weight, not your mass.
so it doesn't tell you how much mass you are, it just tells you how much you're being pulled by gravity.
Exactly. Yep. When you step on a scale, it just tells you how much you're being pulled by gravity. All right, so this would be an aside in the notes. So another force that we will see is applied force. Force applied. I symbolize that just FP, applied force. And applied force is just a generic word for any type of force, right? So if I push on this cart, that's an applied force. If your motor in your car pushes your car, that's an applied force. So examples of applied force would be me push on cart, motor, push on car. Just any other type of force that's not called out and called something else that's pushing or pulling on something can be called an applied force. All right? So I meant to write this out here because I was meaning to write these in the margins. Force applied. Another force is air resistance. So it's big F with the word air as a little subscript. Makes it look like the word fair. Air resistance, which has another name, also known as drag. And so air resistance is created when something is moving through a fluid. So whether you know it or not, whether you're aware of it or not, you are living in a fluid. The atmosphere of air that surrounds you is actually a pretty thick fluid. You're just used to being in it. It's all the time at sea level. It's pushing on you with almost 15 pounds of force on every square inch of your body. So that's a square inch, that's a square inch. All of these square inches are being pushed with 15 pounds. All of them, all the time, ever since you were born. And you're just used to it. You don't notice it. But if we took you out of it, you would notice. Or if you go down deep underwater, then you're in a different fluid, which is pushing on you with a different amount of force, and you notice. Okay? You just happen to live in this fluid, and so you don't notice it. But when you move through it, you'll notice it. If you've ever stuck your hand out of the window when you're driving a car, you'll feel that air resistance on your arm. Or if you're swimming through a swimming pool, you'll feel that fluid pulling on you, slowing you down. So that's drag. We call it air resistance when we're in air, but really drag is more of a general word for any type of motion through any type of fluid. It's going to create an opposing force. So this is an opposing force. It opposing motion. Drag opposes motion. Another force is friction. So like air resistance, friction is friction. Friction is created when two surfaces rub together. And it also opposes motion. One thing that friction depends on is something called the coefficient of friction. And the coefficient of friction is symbolized or written as the Greek letter mu, which looks like a cursive U. It's pronounced mu, like a cat. Mu. It's really this is a small case Greek letter M, but it looks like a cursive U in English. And mu. So mu is basically depends on the material or how sticky the surface is. So if two things are really sticky, they'll have a high coefficient of friction. If things are smooth, they'll have a low coefficient of friction. It's just a number that tells us how sticky things are. And it affects friction. And there's one other thing that affects friction, which is the normal force. So another force is the normal force. I'm almost out of paper here. And normal force. So it's not called the normal force because it's because it's opposed to a weird force or an atypical force or something. It's called the normal force because in Britain, when things are perpendicular to each other, they say they're normal to each other. So this cup, right, the vertical axis of this cup as it rests on my cart is normal to the cart. They're perpendicular to each other. So that's why it's called a normal force, because the normal force is always perpendicular to a surface. And it's created when two things are touching. But not moving. Okay, this is the math symbol for perpendicular. It looks like this. It looks like an upside down T. So that's the symbol for perpendicular. And the normal force is always perpendicular to the, all caps, surface. So for the normal force on this cup, the normal force is perpendicular, pointing out. It always points out. It points outward. Always pointing out. So there's a normal force pushing up on this coffee cup. And it's pointing up perpendicular to the surface. And if I push the coffee cup like this, hopefully it doesn't, that didn't work. Part of the coffee cup will now be played by this ball of string. If I push it like this, now the normal force is pushing out like this. Right? It's that force because you're pressed up against something, and there's a force that pushes out on you. Right? So the force of friction depends on the normal force. If you increase the normal force, you increase the force of friction. All right, so now I've covered an entire page of notes, and I'm going to leave this here. When everybody at your table is caught up, because I need to start a new page, when everybody at your table is caught up, make your cups green. Your cups should be red as long as people are writing these notes. And when everybody's done writing the notes, you can make the cups green. I'm going to turn the camera off, and I'll just start a new one for the next set. We're already at 14 minutes.